Okay, remember we talked about this. So when you want to differentiate something, it's really important that you pre-write it. You got to write it in the way that's going to make the derivative easier to take. So you got to break the layers up so they're obvious. Because right now this is written in shorthand. Really the cube root part's not such a big deal. I mean, we would immediately recognize that this is the first layer of this is a cube root, which is a 1/3 power. That's easy. But the part that people sometimes miss is that, right? You never want to leave it as sine squared. Or if you do, I mean, after you've done a lot of these and you really are comfortable, then you recognize that the next layer is the squared and not the sine. It's just easier to see if you write it that way, right? So this should be, these are the layers, right? The outside layer is all this stuff is being taken to the 1/3, right? What's the next layer? Well, then we've got this polynomial inside, and the next layer is actually, I'll make it orange. Is that, right? The squared is outside of the sine, yep.
Why is it square the whole thing?
Because what this really means, sine squared of x really means this, doesn't it? It means the quantity sine x squared. Okay? So then the next layer is all this stuff is being squared. The next layer is what? What's the next layer inside the power function too? Sine. Yeah, then we get sine of some stuff, right? And what's the last layer? Yeah, the stuff inside the sine. Oops. So how many layers do we have? 1, 2, 3, what is it? 1, 2, 3, 4 layers. Okay. Okay, I put this on here for a reason because a lot of people on the test, with problems like this, they missed a link in the chain. Okay. Pre-writing it is really important. That helps. Okay. Well, okay, yeah, I mean, when we differentiate, what's the derivative of 3? 0, yes. When we differentiate that one, that's just going to go away. Yeah. Okay? That makes sense? Why that's important? Okay? It's always worth doing that. Say it again. Well, then you'd have 1 plus the derivative of all that stuff, right? So it would be part of, I mean, there'd be, I guess, it'd be in the orange layer, I guess, kind of. You know, I mean, yeah. But it would just be, you just get this, you'd get a 1 plus 2 times all that to the 1. Okay? Okay, so for today, I'm going to show you guys. So this is huge. Like chain rule, as important as that was, and it's the most important thing we've learned, this is probably equally important. So implicit differentiation. This makes your life super easy. And in fact, there are some problems, not only would they be very difficult, some problems you just simply can't do using the kind of differentiation that we've done, which we haven't ever called it this, but we've only used explicit methods. Why have they been explicit? Because we've always had y by itself on one side of the equation in terms of x. And so when we calculate the derivative, we calculate y prime, all we have to do is a bunch of stuff with x's in it. But that's not always the case. Sometimes x's and y's are mixed up in relations that may not even be functions. But we still have to be able to differentiate them. Okay? So, what does this mean? So an algebraic function is explicit when the dependent variable, typically y, is written expressed strictly in terms of the independent variable, typically x. Everything we've done has been that way. Every single example we've done. Okay, so the equation is written with y isolated from the very beginning. Okay, An implicit function, on the other hand, is one that is not written as one variable in terms of another variable. Okay? And sometimes it can't be. Sometimes you can't even do that. You may not even be able to isolate the y. Okay, so y is not isolated in the equation. It's mixed up with the x's on both sides of the equation, usually. So let's look at a really simple example. You guys already know how to do this one. Y equals x squared. What's dy dx? Okay, it's 2x, right? It's 2x, and there's an invisible dx there, right? Because first thing we've got is something squared. The derivative of something squared is 2 times something times the derivative of the something, derivative of x, but dx is just 1. So we would never write that. We'd never have had to, but technically it's there, right? Okay. What if we wanted to do, what if we had something like this? Z equals xy squared, and I want to calculate dz dt. Okay, that looks complicated, but you know how to do that. You know how to do that. What do you think I'm going to do there? I'm differentiating. Well, I mean, you got to just follow. You got to follow all your rules. So what pattern do I have to use to differentiate this? Product rule, because it's a product, right? It's a product. So I need the product rule. So that's going to give me x times the derivative of y squared with respect to t. Okay. Plus, oh, that's supposed to be a y squared. Whoops. Plus y squared times the derivative of x with respect to t. Okay? Well, what is the derivative of x with respect to t? It's dx dt. Okay? That one's easy. Okay, what's the derivative of y squared with respect to t? Okay, how many layers are there? There's 2, yeah. Because I'm differentiating this not with respect to y, I'm differentiating it with respect to t. There even was, I mean, even if I was differentiating it with respect to y, there really is an invisible second layer there, right? What if I did that? What's the derivative with respect to y of y squared? Well, the derivative of hand squared is 2 hand times the derivative of what's inside the power function. The derivative of y with respect to y is just 1. So it's just 2y. Right? Because, and so what happened there? Because the variable of differentiation, the variable that's on the bottom of that derivative, is the same as the variable in the function, that last layer always disappears. It's always equal to 1, right? But it's not here. It's not. So what's this going to give me? The derivative with respect to t of y squared, well, what's the derivative of hand squared? 2 hand. So I get times the derivative of what's inside. What's the derivative of y? With respect to t. That's not 1, right? dy dt is not 1. It's dy dt. That's just a derivative. I mean, that's what it is. The derivative of y with respect to t, by definition, is dy dt, right? Okay, you guys have done this. You've already done a bunch of this. I'll give you an example. You've done this before. Like, here's one right here. What's the derivative with respect to x of sine of y? Something like that. Yeah, we could do. What's one we did? Okay, do this one. How many layers? 2. Okay. So what's that equal to? What's the first layer? Cosine of x squared times the derivative of x squared, which is what? 2x times my other invisible layer that we never counted, which is dx dx, which is just 1. Okay? So what if I did the same thing, only now I'm doing that. The only difference is that last layer is no longer invisible, right? I'm going to do the very same stuff I did before. I'm going to differentiate from the outside to the inside. The derivative of sine hand is cosine hand, right? The derivative of what's inside. The derivative of hand squared is 2 hand, right? Well, the first hand was a y squared. The second hand was a y. Okay, now we go one more layer. What's the derivative of y with respect to x? dy dx. I could just call it y prime if I want to. It's dy dx. Okay? See my point? It's the same stuff we've done, but chain rule is something you know how to do. You have to just keep differentiating until you get to the bottom of the thing. Well, now the bottom isn't 1 anymore. The very last derivative we take is the derivative of what's inside everything, which is y, with respect to x. Okay? Think what our chain ruleified derivative patterns are, right? We have all those derivative rules that you memorized. So what is this one? What's the derivative with respect to x of sine u? What was that equal to? There's 2 layers. Cosine u times u prime, or du dx, right? Because when I differentiate, the derivative of sine hand is cosine hand, but the derivative of what's inside the function, the derivative of u, is du dx. Because I'm differentiating with respect to x, right? The derivative of u with respect to x is not 1. It's some derivative. Right? Do you see the pattern? Okay, so then let's finish this one. So the derivative with respect to t of y squared, well, the derivative of hand squared is 2 hand times the derivative of what's inside. What's the derivative of y with respect to t? dy dt. It's not 1, it's dy dt. Okay? What is dy dt? It's the rate of change of y with respect to t. That's all it is. It's a slope if you want to think of it that way, but it's not 1. Okay, plus, what do we get here? We got y squared plus y squared. And what's the derivative of x with respect to t, everybody? dx dt. Yeah, it's not 1, it's dx dt. And that would be our answer. That's the best we could do. dz dt is that. Okay? Now, we're not going to do a lot of stuff like that where we're differentiating 3 variables with respect to some other variable. I mean, we could. It's not hard to do, but that's more of a job for multivariable calculus, which is like a class after this one. But it's not a big deal to do. Okay, but we do need this concept now. Okay, because we need to be able to differentiate, to find derivatives with only 2 variables, x and y, when the x's and y's are mixed up. That is a topic for this year. Okay, but it's the same kind of thinking we just used, or for this high school year. So find the tangent line when x is 3. What would we do? We've got to find a derivative, right? We need a point and a slope, don't we? Well, what's the point? Let's do that real quick. 3, 9. Okay, piece of cake. We need a derivative. Okay, so y prime equals what? So then at x equals 3, what's the slope of the tangent line? 6. Okay, and we got a point, we got a slope, we got this thing, right? So then how do we get our line? Y minus 9 equals times the quantity. There you go. Okay, there's my line. I could distribute and do all that stuff, but I got it. That's my line. And that's what it looks like, right? Okay, there's the graph. We're at the point 39, and we've got the line. There's our tangent line right there. And we just found the equation of that tangent line. Okay? Okay, make sense? Give me thumbs. We good? Okay. Okay, what about this one? Find the tangent line when x equals 9. What are we going to do? Okay, we could. Yeah, we could. So you could isolate y. That's one thing you could do. So if I solve for y, what's that going to give me? Y equals square root of x? Ah, plus or minus the square root of x. Okay, so if I solve for y, how many functions do I get? 2. So I've got to deal with both of those, right? I've got to deal with one of them is y equals positive the square root of x, and another possibility is y equals negative the square root of x. Okay, well, what's our point of tangency? Well, let's calculate a derivative. What's y prime for the first case? That's just x to the 1/2, isn't it?
1/2 x to the negative 1.
Okay, so 1/2 x to the negative 1/2. Isn't that the same thing as 1 over 2 times the square root of x? Right? Okay, so at x equals 9, what's that give us? 1/6. Yeah. Okay, and we've got the point. What's our ordered pair then? So we have a slope. There's our slope for this line. What's our point? 9. And we're taking square root of x. So 9, 3. Okay, so then we get the line what? Y minus 3 equals 1/6 times the quantity x minus 9. Okay, if I distribute the 1/6 and add 3 to both sides, what's that give me? Figure that out. So 1/6 x, what? Minus 3/2 plus 3, so plus 3/2. Everybody agree? If I distribute the 1/6 and then add 3 to both sides, everybody buy that?
Yeah, what did you say?
If I just put this into slope-intercept form, if I distribute the 1/6 and then add the 3, isn't that what I'd get?
I know, sure.
Right? Okay. Okay, but that's only half the picture. Right? That gave us that piece, didn't it? So there's our yellow tangent line. Whoops. Oh, what did I do there? Let's see if I can get rid of that. There's the yellow tangent line. Okay, what about this other piece, though? Look down here. We've still got this one. Okay. I've got to do the same thing with that one because I got 2 functions, right? If I look at the graph of x equals y squared, what does that look like? What's the graph of that relation going to look like? Okay, well, isn't that, so that's like saying y equals x squared, but I'm switching x and y, right? What does y equals x squared look like? Just a regular parabola, right? Okay, what did we say back in Algebra 2 about inverses, right? To create an inverse relation, all you do is you exchange the x's and the y's, and that creates an inverse, right? So isn't that all we did? We just said instead of having y equals x squared,
Oh, so it's gonna go only when it's on.
exactly. So it's going to have symmetry with our original parabola about the line y equals x. That's inverses have symmetry about that line. So we're just reflecting our normal parabola over the line y equals x to get that, right? Okay, so that whole thing is the graph of the relation. It's not a function, right? It's not a function. But if we solve for y, the math gods are wise. If we solve for y explicitly, we got y equals plus or minus the square root of x. And so the math gods, in their wisdom, they did two things. They broke this up into two relations that are functions. The plus version is the top piece, the minus version is the bottom piece, right? But now I've got two problems to solve in one. I've got to go down for the green part of that relation. By itself, it's a function. By itself, the green part or the red part separately are functions. They pass the vertical line test, but together they are not, right? So we go down and we do the same thing. We differentiate that. It's going to look very similar. What's the derivative of negative square root of x? Yeah, just that, isn't it? Right? Negative 1/2 x to the minus 1/2. So just that. So at x equals 9, the slope of the tangent is just negative 1/6, isn't it?
Sure.
Right? And what's our point going to be that we're using on this function? If I plug 9 into that function, I get negative 3. So there's my point of tangency, right? And I could do all the same stuff. I could do point slope. What do you think I'm going to get for my answer? If I do all that stuff, so I'm going to get y minus negative 3. So y plus 3 equals negative 1/6 times x minus 9. Right? So that's going to give me, if I solve this thing, y equals negative 1/6 x. That's going to give me plus 3/2 minus 3 is just that, right? And I get this line right there. Okay? Agreed? It's a lot of work. Can we do that more easily? Yes, we can do it a lot more easily. That's my point is, doing it this way is not a good way to do it. To solve it explicitly for y caused this thing to be really complicated. I had to deal with two separate parts and find two tangent lines independently, okay? What if we do this? So that was our explicit process that we just did. Okay, I'm not going to rewrite it here. Let's do this implicitly. Okay, actually I'm going to do it on this page. Okay, let's do this implicitly. Okay, how could we do that? Well, we had, actually, no, you know what? I remember what I was doing. Never mind, I got to go back a little bit. Okay, I had this for a reason, yeah. Oh, this is kind of cool, actually, now that I remember what I was doing. Okay, we had two things, right? We had y equals square root of x, and we got the derivative y prime equals 1 over 2 times the square root of x. If we started with y equals negative the square root of x, we got the derivative y equals negative 1 over 2 times the square root of x. Do you see a way that we could have defined these as one answer instead of two? I'm going to give you a hint. I'm going to rewrite this one. How could I have combined those into one answer?
Over 2. What would you do? Y. To,
That's what I started with. That's the original function, isn't it? Okay. So I could have written that as y prime equals 1 over 2y. And that's what I originally started with for my function. So I could have written this one as y prime equals 1 over 2y.
yeah.
Okay? Right? How could we get there more quickly? Okay, to get there more quickly, we don't do any of that stuff. We're just going to implicitly differentiate. So all that is, it sounds complicated, but all it means is we're just not going to solve for y. We're just going to differentiate everything with respect to x and see what happens. So we start off with y squared equals x, and we just differentiate both sides of the equation with respect to x. Okay, so what's that give us? On the left side, we get the derivative with respect to x of y squared. On the right side, we get the derivative with respect to x of x. Well, that's an easy one. What's the derivative of x with respect to x? 1. Okay, this one is a little tougher, but we've already talked about how we do that. How many layers are we going to have on this one? 2, yeah. What's the derivative of hand squared with respect to x? I mean, with respect to anything. I get 2y for my first layer, right? Okay, what's the derivative of what's inside that? What's the derivative of y with respect to x? dy dx, which we're just going to call y prime to make it a shortcut. Okay, aren't we trying to find y prime? That's our goal, is to find dy dx, right? Isolate y prime. What's the one algebra step to isolate y prime? Oh, okay. So look what happens. Y prime equals 1 over 2y. I wish I had a mic so I could just drop it right now. How cool is that? Right? That's way, way easier. Okay. Ah, good. That's good when that happens. So let's boil this down. So what are we supposed to take away from all this stuff? What we take away from all this stuff is if we start off with some equation where y is not by itself, you don't have to make it that way. Just differentiate everything with respect to x. That's called implicit differentiation. And when you're all done, isolate the y prime. That's easy to do, because the y primes are never going to be mixed up in an inconvenient way. Think about how we get y prime. Y prime was just the last link of that derivative, right? So the only way we ever get a y prime when we differentiate implicitly is we're going to multiply by a y prime at the end of a derivative. That means that all the y primes are to the first power, right? They're easy to isolate and put on one side of the equation because it's a linear equation. It's not like we're going to have something complicated like this where the y's are buried in some kind of complicated function that makes them impossible to isolate. The y primes will always be easy to isolate. So that's the whole point of this process. So let's practice this. So let's try one like, okay, so now what if we wanted to find the tangent lines? Let's not quite leave this one yet. Let's do our implicit differentiation, which we already did. If we implicitly differentiate, didn't we just get 2y y prime equals 1, right? So y prime equals 1 over 2y. Okay, well then we want to find the points of tangency, and it was when x equaled 9, correct? Okay, so when x equals 9, what is y equal to? Well, that gives us the equation y squared equals 9. If I solve that for y, what do I get for y? Plus or minus 3, yeah. I get y equals plus or minus 3. So think what that means. When x is 9, y is plus 3 or minus 3. So I just get 2 different points of tangency. That's easy though, right? Get 2 points of tangency. Well, what's the slope going to be? Okay, if we're going to choose y equals, if we're choosing y equals 3, then y prime is what? If we're taking the top point, 1 over 6, right? Y prime is 1 over 6, and look what we get then. We get this point with a slope of 1/6, and so it's a piece of cake to come up with that tangent line now. That's algebra 1, right? If I choose y prime, or y equals, let me get a different color. If I choose y equals negative 3, then what's y prime? Negative 1/6. So now I've got another line down here with a slope of negative 1/6, but it's a piece of cake to come up with that tangent line because now I've got a point and a slope. Again, algebra 1. Look how easy we get those. Okay? So let's try questions. I'm going fast here. Questions. Okay, this is going to settle you down if you're thinking, my God, this is a lot of stuff. This will make it easier because this problem is not going to be a hard one. You can do it right now. Find y prime and then tell me what the value is when x equals 1. Go to the boards. Do that real quick.
Okay, I'm just gonna write the first time.